Alright, just a little video here about oxidation of alcohols. Because, again, I've had a little bit of contact from people and it just suggests that there's a couple of misconceptions here around oxidation of alcohols. So I might as well talk through it because it's an important topic. And I'm getting used now to doing these videos a little bit. I know they're not great, but I hope you find some use to them. Alright, so oxidation of alcohols is a really important topic. And you've seen that you need to be pretty good at talking about oxidation of alcohols to answer questions involving infrared spectroscopy. So I'm going to do it really quickly, hopefully quickly. So for me that might be 20 minutes, so I don't know. Right, you all know that there are three types of alcohol: primary, secondary and tertiary, and hopefully you can all draw a primary, a secondary and a tertiary alcohol. I'm going to draw one of each on here. I'm going to draw ethanol. I'll try and be careful with my drawing so I don't miss any bonds. Then I'll do a secondary alcohol. I'll do propan-2-ol. I'm taking care to draw all the hydrogens in. And then I will do a tertiary alcohol. So I'll put the OH in the middle, and then I need to make the carbon that the OH is bonded to. I need that carbon to join to four other carbons. I'll be a little bit lazy here, or lazier. I'm just going to put CH3s in all of these positions. I hope that's okay. Alright. So oxidation of alcohols, you probably know this fact that primary alcohols and secondary alcohols can be oxidized if we add an oxidizing agent. And that's what the square brackets with an O in looks like. Okay, so this is an oxidizing agent. This represents, and we know that, or hopefully you know this already because you've revised it, whether or not you've fully understood it, we know that you cannot oxidize a tertiary alcohol. So you can oxidize a secondary alcohol and you can oxidize a primary alcohol. I like those colours, they look nice, don't they? Alright, and when you oxidize a primary alcohol, what you make is an aldehyde. And again, a lot of you will probably have learned this. So an aldehyde, the aldehyde from ethanol will be ethanal. And what happens is the hydrogen of the OH and the hydrogen of the same carbon will be lost. So you're effectively removing H2. So if you think about removing these two hydrogens, you're left with that molecule. It just needs sorting out in terms of bonds. So there'll be two carbons. It's still eth. These three hydrogens are untouched. I'll just squeeze that in there. It's now a double bond O, and this hydrogen that I'm pointing at here is still there as well. So there's the aldehyde. Same thing happens with a ketone. What happens here is the H of the alcohol is removed, and the hydrogen, another hydrogen off the same carbon. So it's this one here, not off a neighbouring carbon. We're not dehydrating, we're taking a hydrogen off the OH and the hydrogen off the same carbon. So what you're left with, you've still got three carbons in a row. You've got these three hydrogens are still intact. These three hydrogens are as well. And you've removed two hydrogens off that central carbon, so you've got an oxygen there. And to make it all the right number of bonds, it has to be a double bond O. And this is a ketone. Alright, so if you look at the tertiary alcohol and you think, well, why can't this be oxidized? Well, you could remove this H, but the reason it can't be oxidized is there are no more hydrogens on this carbon. So you can't remove another hydrogen off that carbon. If you remove this hydrogen and try to put a double bond O in there, this central carbon would have 1, 2, 3, 4, 5 bonds, which is not right. So tertiary alcohols can't be oxidized. That's a terrible rubber, isn't it? It's made a right mess. Tertiary alcohols cannot be oxidized because they don't have they don't have a hydrogen on the carbon that the OH is bonded to. All right. What then happens is, if you take an aldehyde and you leave it in contact with an oxidizing agent for even longer, you leave it to oxidize for longer, or you have an excess of the oxidizing agent, and you keep it boiling away for a long time. In other words, you put it under reflux, and I'm going to talk about reflux in a sec. The aldehyde will turn into the carboxylic acid. All right, so the same carboxylic acid. So we've got ethanol. When I say the same carboxylic acid, I mean the ethanoic acid. This carbon is untouched. And this second oxidation, the double bond O is still there. It involves putting another oxygen in this position here. So turning your aldehyde into the ethanoic acid. And this happens when you've got excess oxidizing agent and you reflux the reaction mixture for a long time. And the analogy I've used here is that it's a bit like cooking. If you take, I don't know, a steak and you just cook it and cook it and cook it and cook it, you'll end up with a very, very well cooked steak. The aldehyde is a bit like, if you want to have your steak rare, you would have to take it out of the frying pan before it gets all the way to here. So what you have to do, if you want to get an aldehyde, you've got to take it out of the reaction mixture before it can go on and fully cook. Now, excuse the cooking analogy, but I think it works. So this is your uncooked steak, and if you cook and cook and cook and cook and cook it forever, you'll end up with a very, very well cooked steak. And the analogy here is that's your carboxylic acid. But you can, if you're careful, if you cook it for a couple of minutes, you can take it out of the frying pan and you'll end up with this thing called an aldehyde, or a rare steak, using that analogy. So I'm just going to put a tick here so it completes the diagram. Maybe I should have put it there. Oh well. So if you want to make the aldehyde, what you have to do is you have to remove it from the reaction mixture. You have to get it away from the oxidizing agent before it turns into the carboxylic acid. And what we're going to do there is we distill the aldehyde as it forms. And that's the bit I'm going to talk about in a minute. Before I do move on though, this is where the triangle diagram for oxidation comes from that I've been using in my other videos. Not quite a triangle because I ran out of space there, but you can see the idea. And it can be simplified in a lot of different ways, which I'll show you now. So I typically simplify it as this: primary, secondary, tertiary. And for me, that's enough. I know what that means. You could write aldehyde, ketone, carboxylic acid, whatever, however you want to use that in the exam. All right. So other little bits to add. The oxidizing agent that we need to know can be written as H plus K2Cr2O7 in symbols. You could also call this acidified, that's the H plus, potassium dichromate. There's the potassium. There's the dichrome, and it's got oxygen in, so it's 8. Potassium dichrome, and 8 means it's got oxygen in it. So I've just got off the screen a little bit there. I'll try and shift this across without mucking it all up. Okay, potassium dichromate. So that's it in symbols, that's it in words. You can use sodium dichromate as well. You sometimes see it written as potassium dichromate 6 in Roman numeral. Oxidation state of the chromium in this potassium dichromate 6 is 6. So there's something else for the diagram. You need to know is oxidation, the oxidizing agents. You also need to know that potassium dichromate 6 is orange, and then after it has oxidized the alcohol, it turns into green. So in that last video, I was talking about facts that you need to know. So these are facts. You need to know that it turns from orange to green. You need to know that its oxidation state is 6. You need to know its symbols. You need to know its words. You need to know this diagram off by heart. Other facts that you need to know how to name aldehydes. You need to know how to name carboxylic acids. You need to know how to name ketones. So there's quite a lot going on in this diagram, but hopefully this simplification, you can see that if they talk about oxidation of alcohols, you're dealing with this diagram. Right, so what I'm going to talk about now is what these words distill and reflux mean. We have talked about them before, but that doesn't mean that you're going to know about them, because you're trying to teach yourselves, and that's quite tricky. All right then, so I want to imagine then that somebody asks you, now you will be doing a practical on this if we eventually get back to school. How do you make ethanol from ethanol? Okay, so what you would do is you go, right, I'm starting off with ethanol. So you know that you're dealing with a primary alcohol. So the question is asking you, how do you make ethanol from ethanol? It's asking you this. So things to take into consideration, if you're being asked to make ethanol, what they're saying is they do not want you to accidentally make ethanoic acid. So they want you to make ethanol, they want this, but they do not want ethanoic acid. So this is a bit like that analogy about the steak, is you want your steak rare, you don't want it to be overcooked. You don't want them to have taken it all the way to ethanoic acid, which is very vinegary. You want this. So what you're going to do, the way you would set this up, now you might have just learnt it as the word distill, so I want to show you what that means practically. You would take a reaction vessel, something like a round bottom flask. You would take a bung with a hole in it, and you have to be able to draw these diagrams, You would, so to draw this, I'm just going to show a tube coming down here, another tube here. I'll put a thermometer in the end there. Sorry, I should have made this a little bit bigger. And then I'm going to put some cold water going in here, cold water coming out there, and I'm going to have a collection vessel. All right, so what I would put in here is, let's have a little look. Well, I'm going to put in my reactants, my ethanol, and my acidified potassium dichromate. So I'm going to put C2H5OH, ethanol. I'm going to put in some acidified potassium dichromate, and they might write it as H plus Cr2, come on, focus, O7 or whatever, Cr2O7. Or they might write conc H2SO4, that's the acidified, and they might say K2Cr2O7. So that's ethanol and acidified potassium dichromate. They might put it like that. All right, we're then going to add a little bit of gentle heat. And what will happen is, if you look at the reaction scheme, you will firstly make an aldehyde. Now the aldehyde has got a low boiling point. I think these are the values. I'm not going to Google them. I think this boils at 78. This boils at around about 30 degrees C. And ethanoic acid, tell a lie, I am going to Google it. I've got my laptop here. Ethanoic acid, boiling point. Unfortunately, the default search engine on my laptop is Bing, which, as you all know, is useless. Boiling point 118. All right, ethanol boils at 30 degrees C. So if you're heating this up, the chemical reaction happens where the ethanol turns into the ethanal, and the ethanal has got a low boiling point, so it evaporates very easily. It evaporates and goes up this tube and goes around this corner and hits the cold glass and turns into a liquid and drips out at the bottom of the flask and collects here. And the point is, it collects over here and the oxidizing agent is still in the reaction vessel. So it's separating the ethanol out before it has a chance to form ethanoic acid. This is what distillation means. It means you are taking the ethanol out as it forms ethanal to stop it reacting further with the oxidizing agent. So little bits of advice that you'll see in the exam. How can you make sure that you collect more ethanol? You should maybe surround your collection vessel with ice. All right, remember ethanol boils at 30 degrees C, so it's probably best to keep it nice and cool. So that is what the word distill means. You can distill the aldehyde off because it has a low boiling point. All right, so I hope that makes sense. Just a little aside, why does ethanol have the lowest boiling point of these three? Ethanol, ethanal, and ethanoic acid. So there's the three potential products: ethanol, ethanal, and ethanoic acid. Why does ethanal have the lowest boiling point? Okay. Well, if you're dealing with boiling points of molecules, you're dealing with weak intermolecular forces. So all you've got to do is go, right, what intermolecular forces does ethanol have between its molecules? And you would go, it can do hydrogen bonding. Ethanoic acid can do hydrogen bonding. Ethanal can do van der Waals forces and permanent dipole. So ethanal has the lowest boiling point because it has the weakest intermolecular forces, because it cannot hydrogen bond to its neighbours. All right, so that's how you could make ethanal from ethanol. So if you wanted, though, if the question said, how could you make ethanoic acid from ethanol? How could you make ethanoic acid from ethanol? Well, I hope you'd realise, well, if it was a steak, again, it's going back to that maybe bad analogy, I don't know. If it was a steak and it says, how would you make an incredibly well done steak? Well, you would leave it in the pan and you wouldn't remove it from the pan early. So what we're going to do here, the analogy here is, if you want to make ethanoic acid, you don't give the ethanal a chance to escape. You just want to boil it and boil it and boil it until it's done. Okay, so the setup for that is known as reflux. We talked about reflux briefly before. All right, I'm going to draw a piece of equipment here that enables us to reflux the ethanol. All right, so this time I'm not putting a side arm, what do you call it? A condenser, a Liebig, sorry. Let's start off naming these things. This is called a Liebig condenser. So previously I had a Liebig condenser off to the side to enable the aldehyde to escape. This time you put it vertically. So I'm going to put the acidified potassium dichromate mixture in here, K2Cr2O7, and my ethanol. I'm then going to heat it up. All right, there's water going in here and there's water coming out here. You need to know this diagram. This is for reflux. So what happens here is, if you make your aldehyde, the ethanol, the aldehyde will rise up this tube. It'll keep rising up this tube. It will condense and dribble back down into the reaction vessel, and it will go up and down and up and down and up and down. In other words, the ethanol will never be able to escape, so it keeps coming back down. It spends more time with the oxidizing agent, and for that reason, you will eventually turn it into the carboxylic acid. This setup is known as reflux. Reflux effectively means to reboil over and over and over again. And this is the setup that you would use if you wanted to make the carboxylic acid. This, again, just to remind you, very sketchily drawn, is the setup to use if you want to make the aldehyde. All right, you can collect the aldehyde over here. All right, so this is what it's meant if it says if you want to make an aldehyde, you're going to use the distillation apparatus, which is this, and if you want to make the carboxylic acid, you use the reflux apparatus, which is this. So some people on the emails have asked me, well, what if you want to make a ketone? So a ketone is when you take a secondary alcohol and you turn it into a ketone. Well, the thing is, the ketone can't go on to make anything else. So you don't really need to distill it off as it forms. You could just reflux. If you take a secondary alcohol and you reflux it in this setup here with acidified potassium dichromate and boil it and boil it and boil it and boil it, you will make this and it won't go on to make anything else. So reflux is perfectly good for making secondary alcohols. Okay, so we're going to go back now to our diagram. And in fact, let's just have a look at it. So hopefully now you've got a better understanding of what this word means, distill. Distill means give the aldehyde a little, make the apparatus such that the aldehyde can be separated off. Reflux means to boil it away with the Liebig condenser vertically. You could use reflux here. It doesn't matter what you use for the tertiary alcohols, you're never going to oxidize them. All right. So I hope that made things a bit clearer. Yeah, I hope it did. So that's it, and I will see you soon.